In this module, we're going to talk about valence bond theory. It is another theory of bonding, so it kind of goes the next step past what Lewis structures did for the Lewis bonding theory. We're going to build a lot of this on top of the Lewis structures and the geometries that we were looking at. And what we're doing in valence bond theory, we're taking the valence electrons of the atoms, which reside in atomic orbitals, and the knowledge that a chemical bond results from constructive overlap of two half-filled orbitals, and then saying that the geometry of the overlapping orbitals determines the shape of the molecule, and we're going to build structures and pictures off of that. So there are two types of bonds. A sigma bond is when orbitals overlap end-to-end or head-on. So the orbitals have to point at each other, and the lobes that are pointing at each other overlap, and they have the same phase, so they have constructive interference from the wave function. All single bonds are sigma bonds. Pi bonds happen when we have double bonds, triple bonds, and so on. And a pi bond is when you have side-by-side overlap. So for us, that's only going to be p orbitals. So when they overlap side by side. So you would have to have, let's say on one atom, a px orbital, and on the other atom, also a px orbital. So that they would line up side by side on those atoms to overlap. We will see this, like I said, in double bonds and triple bonds. In a double bond, one of the bonds is a sigma bond and the other is a pi bond. In a triple bond, it's still only one sigma bond and the other two are pi bonds. All right, we're doing covalent bonds. So just a recap reminder piece of information. This is constructive interference from the overlap of orbitals, which are waves, on adjacent atoms. So if we looked at H2, right, start with a super simple example. Each hydrogen has one electron in the 1s orbital. If we took the s orbitals on the hydrogens and overlapped them, the probability of finding an electron would be highest in the region of overlap because we're going to have constructive interference between those orbitals. The negative charges are attracted to and stabilized by the nuclei in this area. So that's why even though, right, we're going to start putting electrons together in orbitals and they have negative charges, we're getting a stabilizing effect, which is why the bond forms in the first place. So this seems fairly straightforward. We take the orbitals we have, we overlap it with the orbitals on the atom next to it. Beautiful, done. Of course, it's not that easy, but let's kind of show why. So if we take BeH2, this has 4 valence electrons in this molecule. Up until this point, I could ask you to tell me the geometry of BeH2, and you would tell me that it's linear, and you would be right. So if we're looking at the orbitals that we have available to us, hydrogen just has that 1s. Beryllium has the 2s and the 2p available. So here's beryllium. It has the 2s, right, in my valence that I'm going to look at. If beryllium overlaps with the 2s with hydrogen's 1s to make my first bond between beryllium and hydrogen, it might look something like this. And then when I go to pick a p orbital, right, my p orbitals could be px, py, pz. If I try to use the py, then my hydrogens end up kind of in the same spot. So if we do our best, like still putting things as far apart in space as we can get, I could use the px. So I've got a px on here bonded to the other hydrogen. The other hydrogen has a 1s. But this is wrong. Like if I draw the bonds in, my bond angle is 90 degrees, but we know from Vesper that the bond angle should be 180 degrees. Also, experimentally, both of the beryllium hydrogen bonds are identical. So they should have the same energy. They should have, right, the things about them should be the same. These are not even made with the same orbitals and they give us the wrong shape. So, right, and I've got to also note here, you can only use each orbital once. Once you use an orbital, it's not available to make another bond. Our solution to all of this is that we are going to make and use hybrid orbitals on all non-hydrogen atoms to use for bonding. We will create the hybrids by adding orbitals together to get what we need. And what we need depends on the steric number. So for valence bond theory, we are saying from VSEPR, we know the answer. I know what shape this molecule is supposed to have. How can I mathematically add my orbitals together so that the result is orbitals that point in the directions that they need to make this geometry? All right. Whatever additional reading you do to help you with valence bond theory, please make sure you're following the directions in these videos, not anything that you see in the books for your conventions, for how you draw things, and how you present your answers.